We want to concern ourselves with maximum and minimum values of a function. For that purpose, we'll be interested in functions which are bounded. A function is said to be bounded. F of x is bounded on a set A, and we're going to be interested in the closed interval to begin with. If there is a number m, so that absolute f of x is less than m. We can replace this with less than or equal to m. Finite number so that f of x is less than or equal to m. Then the function is said to be bounded. It'll be said to be bounded above if f of x is less than or equal to some number m, and it'll be said to be bounded below if f of x is greater than or equal to a number minus m. The result that we want, first of all, is that if f is continuous on AB, then f is bounded on AB. And here, the fact that the interval is closed is important. For the definition of boundedness, a function will be said to be bounded on a set if there's a number m, so that it's less than or equal to m in absolute value for each x in the set. All right. We want to take a look at a picture for this. Let's say this is the interval AB. And what we're really going to do is just simply show that the function which is continuous is bounded above. That's to say there's a number m which is larger than or equal to every value of the function. A similar argument will show that it's bounded below. And if you take the larger of those two at absolute value, it will be a bound for the function. This is going to be the first application of the least upper bound property, or the completeness property. Okay, so to make this application, let's let A fix a function f, and let A be the set of x in the interval AB, such that for t less than x, f is bounded above on A to t. The first thing that we want to do here is to show that this set is not empty. That's because A belongs to A. Since A belongs to A is not empty. The reason why A belongs to A is, first of all, there's a value f of A and a value f of B. I don't want to prejudice the picture here by drawing anything in between these, but let's imagine that here's where f of A and f of B lie. And then, given any epsilon greater than 0, in fact, given epsilon equal to 1, there is a delta, so that all the values of f between A and A plus delta are between f of A and f of A plus 1. So here's f of A. And all of them are between f of A and, let's say, f of A plus 1. Okay, so that means that there is, at least on the interval from A to A plus delta, where delta, of course, depends on A, f is bounded. So the set A of x, where the function is bounded above t less than x, is not empty. And since we're only looking at x in the interval A to B, A is bounded above by B. All right? B is an upper bound for A. And so consequently, this set A has a least upper bound. And let's let x naught be equal to the least upper bound of A. Now, we want to show that x naught is b. To do this, let's suppose that x naught was less than b. If x naught is less than b, then what happens? Well, there's another delta for x naught. So that if we look between the interval from x naught minus delta to x naught plus delta, f is no larger than its value at x naught plus 1. Between x naught minus delta and x naught plus delta. But now f was bounded on a to x naught minus delta, and so consequently it has to be bounded on a to x naught plus delta by taking the larger of the two bounds for on a to x naught minus delta and on x naught minus delta to x naught plus delta. Or to x naught plus something a little larger than x naught but less than delta. Right? So consequently, on this interval here, for a suitably chosen delta, f is bounded. And so consequently f is bounded over to x naught plus delta. And so that x naught cannot be less than b. Thus, x naught is equal to b. Right? This is a problem here, so x naught must be equal to b. Now we want to show that f is bounded on the whole interval AB. Right? And the reason for this is the same type of argument. There is a value f of b, and if we go appropriate delta to the left of b, the function is no larger than f of b plus 1. Right? But we know it's bounded from a up to this point, and it's less than or equal to f of b plus 1 on this interval here, and so by taking the larger of the two bounds for the function, we find that the function is bounded above, so that f is bounded on AB. Right? So we have then the following results. If f is continuous on a closed interval AB, then f is bounded on AB. And the fact that this is a closed interval is really important. If we were to use, for example, an open interval, the result would not hold. In particular, for example, if we take the function 1 over x on, let's say, the open interval 0 to 1, the function looks like this and is not bounded above. So that the closed interval is important. Right? Open will not do. Okay, so this is the first resultant along this line that a continuous function on a closed interval is bounded on that interval. Okay, now we want to look at maximum and minimum of functions. A point x naught, right, this is a little bit confusing, but it's the terminology that's used frequently. The maximum of f of x on, again, we're going to be interested in closed intervals, but this would make sense on any set, on AB, if f of x is less than or equals to f of x naught for all x in AB. If f of x is strictly less than x naught for all x except for x naught, then it's said to be a strict maximum. Similar definition holds for the minimum. Right? A point x naught is the minimum if f of x is greater than or equals to f at x naught for all x in AB. This is the minimum on the interval AB. So, those are two definitions, maximum of a function and minimum of a function. Now what we want to see is that if you've got a continuous function on a closed interval, that it takes on its maximum and its minimum on that interval. And again here we're just going to look at the maximum. The minimum is gotten similarly by considering the other direction. That's a picture again. Say this is A, B. And we have f of x in here. Perhaps this is f of A and this is f of B. But again, we don't want to prejudice the issue by trying to see what f might possibly look like between A and B. Okay, well we know now that f is bounded above. So if we look at the set B, we let B be equal to the set of y such that there is an x in AB with f of x equal to y, then B is an empty, because f of A is one of these points. All right. And B is bounded above, and so we can let y naught be equal to the least upper bound of the set B. So here might be y naught. The function is never any larger than y naught on the interval AB. Now what we want to do is we want to show that there is a point in the interval whose value is y naught. Okay? Possibly f of A is y naught, in which case we're done. Otherwise, f of A is not y naught, and it has to be something less than y naught, because y naught is the least upper bound on the interval. It's the supremum of the values on the interval. Okay, let's consider another set here. Again here, this is going to use the completeness argument. It already has, and it's going to do again. Let C be the set of x in AB, so that for t less than x, f of t is less than y naught. Okay. Now C isn't empty because A belongs to C, and for that matter, what? Since the function is continuous, there's a small delta here, so that f of x is less than y naught when x is between a and a plus delta. You can see this by choosing epsilon to be half of the distance between f of a and y naught. Then there has to be some small delta over here, so that f of x is less than that. So a is in here. And for that matter, a is not equal to the least upper bound of this set, unless f of a was y naught. Now what we want to do is we want to let x naught be equal to, the set's not empty, it's bounded above by b, and so let x naught be equal to the least upper bound, or supremum, of c. This is going to be our x naught. And for that number x naught, we're going to claim that f of x naught is equal to y naught. Right? F of x naught can't be larger than y naught, so there's only one other possibility. If it's not larger than y naught, it possibly is less than y naught. So suppose f of x naught is less than y naught. Okay, well then, again here, if this is f of x naught, right, there is a small delta here, so that if x is between x naught minus delta and x naught plus delta, f of x is less than y naught. In fact, if we choose epsilon equals to half the distance between y naught and f of x naught, then we can insist that it be less than that quantity plus f of x naught. All right? Well, if x naught is located here, then what this says is that f of x naught is not the supremum. You can move a little bit to the right-hand side here. So if x naught is between a and b, and f of x naught is less than y naught, then this is a contradiction. And so in this case, f of x naught is equal to y naught. Right? That's if x naught is in a to b. Right? The other possibility is that x naught is equal to b. And if x naught is equal to b, the same argument shows that f of x naught can't be less than y naught, because if it were, if this was, let's say, f of b naught, it's been drawn considerably lower here, then what? There would have to be a small interval to the left of b minus delta, so that f is smaller than y naught on this interval. In fact, it's considerably smaller. And since it's smaller on the interval all the way back to here, it's going to be smaller altogether than y naught. And so if x naught happens to be equal to b, then we find that y naught is not the least upper bound on the interval ab of the values of the function f. There's a smaller one, because there's it's not the upper bound on this interval, least upper bound on this interval, and it's not the least upper bound on the interval prior to that. That's because for all these values back here, the function is definitely less than y naught. Right? So if x naught is equal to b, then f of b must be equal to y naught. So if f of a is y naught, we're done. If f of a is not y naught, but x naught is in ab, then we're done. F of x naught is y naught. And if x naught is equal to b, then f of b is y naught. And so in any case, the value of the function at some point, x naught in the interval is equal to y naught. Now, the fact that this is a closed interval is important again. For example here, if we let y equal x squared on the open interval 0, 1, right? Then we find that the graph of this looks like this. And the function does not take on either its maximum or minimum on this open interval. We can always find points. If it took on its maximum, let's say at a point here, that can't happen because you can always find points further to the right where it's larger. And if it took on its minimum over here, that can't be the minimum because you could always find points to the left where the function x squared is smaller. So the closed interval here is important. Okay, we now want to take a look at a situation where f does not take on its minimum or maximum at a particular point. That is to say, if x naught is in the open interval AB. And a derivative exists at x naught and it's greater than 0, or the derivative is less than 0. All right. So in particular, if the derivative is not equal to 0, then x naught is not the maximum of f on AB. It's also not the minimum. Okay. The picture for this looks something like this. Here's the interval A, B, and here's x naught. And there's perhaps f of x naught, and now the derivative is, I'm going to assume first of all that the derivative is greater than 0. So this would be the slope of the tangent line, if you want, to the graph of this. And what we really want to show then is roughly that, okay, to the right of this point, the function is larger than it is at x naught. So here's f of x naught. And to the left, it's less. And so this can neither be a maximum nor a minimum. All right? The function, of course, does not have to look this nice. It just has to have a derivative at the single point x naught. However, if it does, then what? The derivative at x naught is equal to the limit as h approaches 0, f of x naught plus h minus f of x naught over h. And this is greater than 0. Right? So there is a delta. Right? So that if we stay nearby here, this quantity is close to this one, and so it must be greater than 0. So this is so that if h is an absolute value less the delta, then f of x naught plus h minus f of x naught over h is greater than 0. Because this is its limit and it's a quantity which is greater than 0. If you want, let epsilon be equals to half of the difference between f prime of x naught and 0. Half of f prime of x naught. And then for the delta corresponding to it, you will get that this must happen. Right? Now, if h is greater than 0, then we can multiply both sides of this inequality by h, and we get f of x naught plus h minus f of x naught is greater than 0. Or, that's to say, f of x naught plus h is greater than f of x naught. And so that shows that this cannot be the maximum, because f of x naught plus h for small h over to the right here is larger than f of x naught. It may not have to stay larger for long, but it's definitely going to be larger for a small enough h to the right. And similarly, if h was less than 0, if we multiply it by h, we're going to get the opposite inequality, and we're going to get f of x naught plus h is less than f of x naught for h to the left of x naught. So this can't be the minimum either. Right? And now a similar picture holds if the derivative happens to be negative. That's to say, here's a and b, and if this is x naught, and if the derivative is negative, then the slope of the tangent line is like so. Right? And values to the left of x naught, a little bit, will be larger than the value at x naught, and values to the right of x naught will be less than the value at x naught. And so consequently, the function cannot take on its maximum or minimum at any point in the interval where the derivative exists and is either larger or less than 0. That's to say, if it does take on its maximum or minimum, the derivative at that point at a point where the derivative exists, the derivative has to be equal to 0. All right, now we want to consider any function whatsoever on a closed interval a, b, and we want to look at what could possibly happen with respect to maximum and minimum. And this is what can happen. Right? If f of x is defined on AB, then f can take on its maximum value or minimum value only at points x dot where one of three things happens. One, x dot is one of the endpoints of the interval. X dot is A or x dot is B. Secondly, another possibility is that the derivative at x naught does not exist. Abbreviate that with DNE. Derivative does not exist. And thirdly, the derivative at x naught is equal to 0. Those are the only three possibilities. And to see this, one only needs to consider all the possibilities. All right? Let's consider the x in AB, the closed interval. Well, there's two possibilities. X is equal to A or B, or the other possibility is that x is in the open interval AB. Well, let's make this x naught maximum, or possible maximum for the function. Okay, if x dot is in the open interval AB, there's two possibilities. The derivative of f at x dot does not exist, and the derivative of f at x dot does exist. Right. Well, this is one of the possibilities. This is one of the possibilities. And if the derivative does exist, there are two possibilities. The derivative at x dot is equal to 0, and the derivative at x dot is not equal to 0. Right? We already showed that the maximum or minimum cannot occur here. So that means that it must occur at either here, here, or here. That's to say, the only points where the function can take on its maximum value or minimum value on an interval are, on a closed interval, are the endpoints of the interval, A and B, or places where the derivative doesn't exist, or places where the derivative is equal to 0. Now, frequently, there are only so many of those points. And so, consequently, you can find where a function takes on its maximum or minimum, and in particular, let's say if the function is known to be continuous, you know it takes on its maximum or minimum. You can find this by just checking these points, where x naught is A or B, the endpoints of the interval, where the derivative doesn't exist if there are any points like that, or where the derivative is equal to 0. If there are only finitely many such points, at whichever point the function is largest, that's the maximum for the function, and at any point where the function is, of those points where the function is smallest, that has to be the minimum for the function. Now we're going to use this for some applied problems in maxima and minima. Before talking about or giving some examples of particular max-minimum problems, I want to outline just exactly how such problems can be solved, or one way at least in which they can be solved. This is going to be the thing that we're going to try and find when we know we're dealing with a maximum or minimum problem. So an outline looks like this. First of all, write down all the equations which are known about the problem. Then that would be a natural thing to do, of course. But then the second thing to do is to try and write the quantities to be maximized or minimized as a function of one variable. All right. So you use these equations that you've written down that are known about the problem, and you try and solve them for the quantity to be maximized or minimized, and particularly you'd like to find that when you do this, that you've got it as a function of one variable. And the third thing, and this is important but often neglected, find out the interval on which the function makes sense. That's to say, makes sense for the problem. Now, sometimes this will be a closed interval, sometimes an open interval, sometimes an interval from quantity to infinity, or sometimes the entire real line. But you want to know the interval on which this makes sense. If it's a closed interval, then you can apply the result which was just gotten, namely that the function can only take on its maximum and minimum at certain points, namely where the derivative is 0, doesn't exist, or the endpoints of the interval. So then, fourth, the next thing to do is find where the function takes on, if it does, its maximum and minimum on the interval. When we do some of these problems, it'll be clear as to what exactly is meant by doing this type of thing here and when you can conceivably do it. You can get a sense for when you can do it. For example, if you can write down all the equations and you feel you can solve them for the quantity to be maximized or minimized, and then it's important to find out, all right, where does this problem make sense? For this one variable does the problem make sense? And then find where the function takes on its maximum or minimum on the interval where it makes sense. Huh? All right, presumably it's going to make sense on an interval. Right, so this is the way to solve max-min problems, and a few examples will refresh one as to what exactly this means. Okay, so for a first example of a max-min problem, we want to consider the following. So let's imagine that this is a river up here, right? And that a farmer has 200 feet of fencing. Right? And he wishes to make a rectangular pen here along the river. And he wishes to do it so that the area A, well, not a pen perhaps, but enclose this area here with A maximal. Right. We need to find out what A is. Okay. Well, if we let this one side of the fence should be x, and the other one is then going to be x, and this is going to be equal to y, then we know that the area is equal to x times y. And we also know that x plus y, or 2x plus y, is equal to 200, the total amount of fencing. So here we've written down two equations that are known here. This is the quantity to be maximized, and we want to get it as a function of one variable. Well, it's got two quantities that vary here, x and y. However, if we solve this for y, we find that y is equal to 200 minus 2x, and so that the area is equal to x times 200 minus 2x. And now we have the area as a function of one variable, namely a of x is equal to 200x minus 2x squared. All right? Now the next thing to do is to determine the interval on which this makes sense. And sometimes the problem, well, it makes sense on the interval, sort of. It doesn't really make great sense at the endpoints. One possibility here, for example, would be to let x equal 0 and run the fence down the river. All right? So that you could let x be as small as 0, but obviously you do not want a negative x for this problem. The other possibility would be to let x be equal to what you'd get if you ran the fence out, turned around, and went back. That's to say, if x was equal to 100. All right? Every value of x between 0 and 100 then is a possible place where this might take on its maximum. So here's the interval on which this makes sense. Now we want to find out where it takes on its maximum on this interval, and it's not at the endpoints. A of 0, we put 0 in here, is equal to 0, and this is also equal to A of 100. Putting 100 in here, or just observing that if you let this run out 100 and back 100, you get no area in between. Right? The function is differentiable at every point in the interval, so the place where it's going to take on its maximum and minimum has to be someplace where the derivative is equal to 0. So we take the derivative, which is 200 minus 4x. We want to know when is that equal to 0. Right? I put it equal to 0 in parentheses here to indicate that it's not always equal to 0. We want to know when it's equal to 0. And it's going to be equal to 0 when 200 is 4x, or when x is equal to 50. And when x is equal to 50, y is 100. Huh? So the way to maximize this area is to run this out 50 feet over 100 and up 50, and the resulting area you're going to get is going to be 50 times 100, or 5,000 square feet. Okay, so there's the first example of a maximum minimum problem. Okay, a second example. In this case here we want to make a box from an 8 by 10 piece of cardboard. As follows. We want to take the piece of cardboard like so. We want to cut square corners out of it. And the remaining shape we will fold on these lines like this to make an open box. And the idea is to do this with maximum volume. so that if we cut out x here, this is going to be 8 by 10. We're going to end up with a box that looks something like this. It's going to have x for its height. Its narrowest side is going to be 8 minus 2x. 8 minus the 2x's that are cut out here. And its longest side is going to be 10 minus 2x. So the volume of this box is going to be equal to x times 8 minus 2x times 10 minus 2x. Right? So we already have this volume V, which is to be maximized as a function of one variable. Let's multiply it out here. This is equals to, what? 80 minus 20x minus 16x. So that's minus 36x and plus 4x squared. We want to multiply this by x here, so that this is going to become by 4x cubed. This is going to become 36x squared, and this is going to be 80x. So there's the volume as a function of one variable. The next thing is to determine the interval on which this makes sense. And how big could we let x be? Well, certainly x could be 0, in which case we would have a flat piece of cardboard still, and it wouldn't have any volume. But we could let x be in the interval from 0 all the way up to 4. When x is as large as 4, then you basically cut the two corners off and fold the middle up, and you've got no box whatsoever. But in this interval here, making a box like this makes sense. It's kind of silly at the endpoints, but nonetheless it makes some sense there. And so we could talk about this being, we want to find out where this takes on its maximum on this interval. And then a thing to note here is that v of 0 is 0 if we put x equals 0 in here. And also, this is the same thing with v of 4. It's equal to 0. You can see that right here. 8 minus 8 will be 0, and so v of 4 will be 0. So we don't really need to check the endpoints of this interval to find out where it takes on its maximum or minimum. So the derivative, well, this is equal to what? 12x squared, going this way, minus 72x plus 80. We want to know, when is this equal to 0? Derivative always exists, so that the maximum of this function on this interval can only occur at places where the derivative is equal to 0. It doesn't occur at the endpoints. All right. Well, I guess we can divide this through by 4 to simplify things. Here we get 3x squared minus 18x plus 20. We want to know, when is that equal to 0? And it's going to be equal to 0 when x is equal to 18 plus or minus the square root of 18 squared minus 4 times 3 times 20 over 6, 2a. Right? So here are two candidates for the maximum and minimum. The thing to do is to make sure that they lie in the interval. Let's see what happens here. 18 squared. Okay. 144 and 18 is 324. So 18 squared is 324. 4 times 3 is 12 times 2 times 20 is 240. Yeah? So 324 minus 240 leaves us with 84. So this is equal to 0 when x is equal to 18 plus or minus the square root of 84 over 6. Right? That's to say, at 3, plus or minus the square root of 84 over 6. 3 plus or minus the square root of 84 over 6. Well, the square root of 84 is a little larger than 9, and so this is about 1.5. And 3 and 1.5 is outside of the interval from 0 to 4. So it can't be the plus part here. It has to be the minus 1. So here then is the value x, where the volume V is maximal. Okay, another example. The examples here, of course, are always dependent upon geometry because that's part of mathematics, but it's clear that you can use the same type of operation in physics or any other subject matter, economics, psychology, sociology, whatever, where you've got a maximum problem that involves equations. I'm going to look at an example here as follows. Let's suppose we want to make a swimming pool, like so. And we want to make the swimming pool so that its shape is reasonable. We're going to determine that when we're done. And so that there are 3 feet on each side here. But at the deep end of the pool, or the patio end of the pool, there are 10 feet. And we want the swimming pool to have 400 square feet in area. We want to do this with the following idea, that the patio costs $9 per square foot. And the pool costs $18. Right? So we want to do this with the idea of minimizing the cost involved. Now, clearly this is a simplified example, but you could have a more complicated example with each of the 4 walls of the pool and the floor costing various amounts, and reduce the thing to the same type of problem. Okay, so what is the total cost? Oh, well, let's also assume that we're going to put some limitations on this, namely that this is going to go on a lot that is 60 feet wide. So we do not want the entire width of the thing to be larger than 60 feet. Right. The cost then, if this side here is x, and this side here is y, what? The cost is going to involve the patio. And the patio is going to have for its dimensions x plus 6 and y plus 13. So this times $9, and then another $9 times 400 for the extra cost of putting the pool in. The pool costs $9 more than the patio. So this is the total cost. Now we want this as a function of one variable, and another thing that we know is that x times y is equal to 400, or y is equal to 400 over x. So we could write that the cost is a function of x as 9 times x plus 6 times 400 over x plus 13 plus 400. Okay, and we need to check the interval on which this makes sense. The interval is going to be, x can be as small as 0, which is obviously not going to be the best cost here, because 400 over x will be very large, and this will be close to 6. Or it can be, we actually won't get a pool in that case, huh? Or it can be as large as what? 60 feet less than 6, or 54 feet. There's the interval on which this makes sense. So we're going to need to check 54. All right. It's really doubtful that 54 is going to be the answer to this, though, and I'm not going to bother to really check it. Now, on this interval, then, we want to find out where the function takes on its maximum, so we want to check the derivative. And the derivative is equal to 9 times, what is the product, so it's the first, times the derivative of the second. 400 over x, the derivative is 400. Derivative of 1 over x is minus 1 over x squared. Plus the second times the derivative of the first. 400 over x plus 13 times the derivative of the first is 1. Right? And the derivative of 400, of course, is 0. So there's the derivative of this function. Now we want to find out when is this equal to 0. Right? It's going to be equal to 0. We can forget about the 9 here and multiply this through by x squared, in which case we're going to get, let's multiply it by minus x squared. We're going to get, it's going to be equal to 0 when 400x plus 2400 minus 400x multiplying by minus x squared minus 13x squared is equal to 0. Well, 400x minus 400x is nice. So we get 13x squared must equal 2400, or x must be equal to the square root of 2400 divided by 13. Let's see, 13 into 2400 is about 200, and the square root of 200 is about 14. So this is going to be about 14 feet. And when x is about 14 feet, y is going to be, since x times y is 400, is going to be about 30 feet. So 30 is approximately equal to y. And now if these were pleasing dimensions, one might consider making the pool with these dimensions, because these are going to be the dimensions, these essentially, which can give the least cost. Of course, one also should check 54, but that's not a likely candidate for the minimum. Another example here. Let's suppose that it is desired to make a trough, like so, with two 4-foot sides, so that and length L, so that the resulting volume be maximal. And the question is to determine what angle theta one should make this trough at. This comes down to the problem of finding at what angle theta is this triangle, is the area of this triangle maximal, where the two sides are 4 feet. Well, if this is the base B of the triangle, then let's draw this like so, and this is the height h, and this is B over 2, and B over 2 here. And then what we know is that the area of the triangle is equal to 1/2 the base times the height. And this is what we want to maximize. Okay, and there are some other things that we know here then, right? H over 4 is the cosine of 1/2 of theta. And B over 2 over 4 is the sine of 1/2 of theta. All right, so that H is 4 cosine theta over 2, and B is 8 sine theta over 2. And so that the area is equals to a half the base times the height is going to be 16 sine theta over 2 cosine theta over 2. Now this is going to make sense when theta is between 0 and 2 pi. 0 and pi. And clearly at the end points here when theta is 0, you end up with no area. And when theta is equals to pi, you've got a straight angle here then, and there's no area between for the triangle. So we don't need to concern ourselves particularly about the end points, although we want to make sure that we stay within that interval. So here's the function here. It's differentiable function for all those thetas. So the derivative is going to be equal to 16. And now this is what? Sine of theta over 2 times derivative of cosine of theta over 2, which is minus sine of theta over 2 times a half. Derivative of theta over 2. Plus the second here, cosine of theta over 2. And the derivative of sine of theta over 2, which is cosine of theta over 2. So we have cosine squared of theta over 2 times the derivative of theta over 2, which is a half. Right. So now we want to know when is this equal to 0. It's going to be equal to 0 here. We can disregard the 16. And we can also disregard the halves here. It's going to be equal to 0 when what? Minus sine squared theta over 2 plus cosine squared theta over 2 is equal to 0. Or when sine squared theta over 2 is equal to cosine squared theta over 2. Or when tangent squared theta over 2 is equal to 1. Or when tangent of theta over 2 is equal to 1, and the tangent is equal to 1 when the angle is 45 degrees. So that we get theta over 2 is 45 degrees, or theta is equal to 90 degrees. So the correct way to make a trough here with the maximum volume is to put an angle at the base here of 90 degrees. All right, we want to do an example now that's a little bit trickier, perhaps. The idea is this. We imagine a corridor here, 3 feet wide, that opens to a 6-foot wide corridor. And what we wish to do is we wish to determine how long a pole can be slid along the floor here, so that you can make this turn. Obviously, if the pole is too long, the turn can't be made. Okay? Let's put this over here, I guess. 6 foot. And here's the picture. You want to know what's the length L of such a pole. And so at first glance, this looks like as if it is a maximum problem. You want to maximize the pole that can be slid along the floor in the corridor. However, it turns out to solve this, you want to use a minimum approach. Let's look at the problem. These two triangles here, or these two triangles, preferably perhaps, the whole pole has got length L. These two triangles with this angle theta here are similar. And if this length is L1, and if this one is L2, then L is equal to L1 plus L2. And we also have that, 6 over L1 is equal to sine of theta. And 3 over L2 is equal to cosine of theta. So we can combine these then to write that L, what do we have here? L1 is equal to 6 over sine theta, that's to say 6 cosecant theta. L2 is 3 over cosine theta, that's to say 3 secant theta. And so that L is going to be equal to 6 cosecant theta plus 3 secant theta. And that's when you have got a pipe or a pole here that is exactly at this angle theta. And now, whatever length we have here, we're going to need it to be small enough so that it can make this turn. That's to say we're going to want to minimize these numbers L, all the numbers that can be gotten by putting a pole in here at a particular angle theta. So this really turns out to be a minimizing problem in order to find out what's the largest length L that you can have for such a pole. All right, and then now what's the interval in which this makes sense? Theta can be between 0 and pi over 2 in order to get a triangle here that's needed to make the turn. And we want to find the minimum length on this interval, and it's clear here again that at the end points, the minimum doesn't exist. In fact, you can put as large a pole as you want with a 90-degree angle, or this way with a 0-degree angle. All right. So now we have L of theta, and we want to compute L prime of theta. It's going to be equal to 6 minus 6 cosecant theta cotangent theta plus 3 secant theta tangent theta. So the derivative here exists on the interval, and we want to know then where is the derivative equal to 0. The endpoints are clearly not going to be the solution here to this problem, and this is going to be equal to 0 when 0 is equal to, let's say, dividing by 3 here, minus 2, and let's rewrite this in terms of sines and cosines. So this is 1 over sine theta and cosine theta over sine theta plus 1 over cosine theta sine theta over cosine theta. So when 0 is this, or when, 2 cosine theta over sine squared theta is equal to sine theta over cosine squared theta, or when 2 cosine squared theta, cosine cubed theta, multiplying by cosine squared, is equal to sine cubed of theta. That's to say when dividing by cosine cubed here, when we get 2 is equal to tangent cubed of theta, or when tangent of theta is the cube root of 2, or arctan of the cube root of 2, the angle whose tangent is the cube root of 2. Then if you take this quantity right here, this is the theta, you put it back in here, you will find the value L, which gives the largest length that can be moved completely around this corridor into the other corridor. Okay, we now want to consider some examples where the interval is not necessarily a closed interval, and sometimes where the interval is not a bounded interval. And what you need to do in those cases is you need to look at what happens as the variable gets close to the ends of the interval, or perhaps gets very, very large. Let's give an example here. Let's suppose again that this is a river. Right? And now we've got a farmer here who wants to enclose an area of 100 square feet. And he wants to do this, so the area is going to be equal to 100 square feet, and he wants to do this with a minimum amount of fence. And the question is, what dimension should he use for the fence? Well, if this is x, and this is y, and this is x, then the fence is equal to 2x plus y. And we know that the area is equal to 100 is x times y. So we can write the fence as a function of one variable, because what? 100 over x is equal to y, right? And so that the fence as a function of x is equal to 2x plus 100 over x. Right? Now what's the interval on which this makes sense? Well, x could be very small, in which case you'd run this very long along the river, so all the way down to 0, right? And we could actually consider this as including 0 here, although it doesn't make sense here because the amount of fences could be infinite, or if you like, this could be very large as x gets close to 0. And x could also be very large and run the fence down this way very long distance and then turn around and go back, so x could be as large as you like. But now if you look at the problem here, you see that when x is very small, the 100 over x is going to make the amount of fence very large. And when x is very large, the 2x is going to make the amount of fence very large. So we really don't have to concern ourselves with the endpoints of this interval, because we've looked at what happens as you approach either endpoint. All right? What's meant by that exactly will be made more precise when we talk about graphing functions. At any rate, this function here is differentiable at every point in this interval, and the derivative is equal to 2 plus 100 times minus 1 over x squared. And we want to know when that's equal to 0. It exists except that x equals 0, and so we're interested in it. And that's not a meaningful point in the interval here, so we want to know when this is equal to 0. It's going to be equal to 0 when 2 is equal to 100 over x squared, or when x squared is equal to 50. When x is equal to the square root of 50. Right? So this says that x should be the square root of 50. This is going to be the square root of 50, and since the entire fence is going to enclose 100 square feet, we need what? 2 times the square root of 50 here for y. Right? This makes sense with the previous problem where we found out that if we had a fixed amount of fence, we wanted to maximize the area, we should make y twice as large as x. Okay, but here's an example of a problem where the interval could be extended indefinitely. However, the problem really here doesn't make sense near the ends of the interval. Okay? In fact, it's at 0 and at infinity near those ends where you can get the maximum amount of fence rather than the minimum amount. Okay. Okay, let's look at another problem of that sort. Let's suppose that we wish to make a stained glass window here. And it's going to look like this. It's going to have a rectangle for a bottom and a circle for the top. And we want the whole window to have 40 square feet. So the area is going to be equal to 40 square feet. And we're going to put some sort of a decorative arrangement around the outside here. And to keep the cost down, we want to minimize the perimeter. So to minimize the amount of perimeter to the window. Well, if this is H, and this is R, and this is R, and this is R, then the perimeter is going to be 2H plus 2R plus, 2 pi R would be an entire circle, so it's going to be pi R. Okay. And, all right, there's the perimeter. And now we know that the area, which is 40, is supposed to be, is going to be what? 2R times H plus pi R squared over 2. The area of the rectangle and the area of the semicircle. So what we want to do with this then is to, let's say, solve this for H, getting what? 40 minus pi R squared over 2 over 2R is equal to H. Right? We then have that the perimeter is equals to 2 times this, which is 40 minus pi R squared over 2 divided by R, plus 2R plus pi R. Okay. Now here's a situation where R, since we've solved this for R, we've got the perimeter as a function of R. R makes sense. If you had a large enough R, you would have all semicircle and no height. So R would make sense between R equals 0. H makes sense between 0 and infinity. But R makes sense between R equals 0 and it doesn't make sense at the end point. And what? R can be so large so that we get all semicircle. That's to say, when 40, which is the area, is equals to pi R squared over 2, or when 80 over pi square root is equal to R. And that's a possible point to check. 0 is a possible point to check. Perhaps when, obviously 0 is not going to work here, because if you make R equal to 0, you're going to have a lot of H. And consequently a lot of perimeter. But this is a possible point to check. To find the other points that need to be checked here, we want to differentiate this and find out where the derivative is 0 or where the derivative doesn't exist. Right. We get 40 over R, so that's going to be minus 40 R to the minus 2. 40 times the derivative of 1 over R, which is minus 1 over R squared. We've got minus pi over 2 times R, so that's going to be minus pi over 2 plus 2 plus pi equals 0. Right. So this is 40 over R squared. This is going to be equal to 0. It's going to be 0 when 40 over R squared is equal to what? 2 plus pi over 2. Or when r squared is 40 over 2 plus pi over 2, or when r is the square root of 40 over 2 plus pi over 2. So here are 2 points to check, this one and this one, to determine where the maximum occurs, or the minimum perimeter. Whichever of these 2 points, the value of p is smallest, that's the minimum. All right, another example of a max min problem here is going to be the following. Let's suppose that we wish to make a tin can. We want to make this up with a fixed volume V, but with the least amount of materials. So V is fixed, and the question is, what dimension should we make this? What should be the radius of the base, and what should the height be? So we know that V is equal to pi r squared h. But the quantity we want to minimize is A, which is what? If we rolled this tin can out, we would find that we would have a piece of metal 2 pi r in length and h in width, and then there are the 2 pieces for the top and the bottom, so that's going to be 2 pi r squared. So this is the area. Now we want this as a function of one variable, and here, if we solve this for h, since v is fixed, we then have that the area is equal to 2 pi r, and h is v over pi r squared, plus 2 pi r squared. All right, the interval on which this makes sense. You could consider this as being the interval from 0 to infinity. If r was very small, we end up with a very pole-like tin can, and if r was very large, we end up with a very flat saucer-like one. However, at the end points here, we have area as a function of r at 0, and for large values of r are not where the minimum is going to occur. Area as a function of r is what? 2v over r plus 2 pi r squared. So when r is very large, the area is going to be large. That's clear from this. And when r is very small, the area is going to be very large also, from 2v over r becoming large. So the minimum is not going to occur for either large values of r or for small values of r. Is going to occur somewhere in between. And so we can use our standard methods here for finding where the minimum occurs. Namely, we look at the derivative of this function. It's 2v times minus 1 over r squared plus 2 pi times 2r. We want to know when is that equal to 0. And it's going to be equal to 0 dividing by 2 here, I guess, when v over r squared is equal to 2 pi r. Or when v is equal to 2 pi r cubed, or when r is equal to the cube root of v over 2 pi. From this r here, and the fact that this is the volume, we can find out what h happens to be. Right? And curiously enough, if you do this, you will find that h is 2 times r. That's to say, this height here is 2 times the radius, or the resulting tin can with the minimum surface area is going to look like a square when looked at directly. This is not particularly pleasant shape, and is not frequently the shape that the tin cans are made in unless they contain large quantities of a substance. Another Max-Min example. Right after this, we'll generalize this to a slightly wider case and indicate how you can solve things that cannot be reduced to a function of one variable. But for our purposes here, let's suppose we were supposed to make a box with an open top and square base. And volume V. With the least amount of materials. So the box is to look like this. It's going to have a square base and a square top, and it's open on the top, and looks like so then, huh? So that if this is X, this you can write as X, and the height is Z, huh? And so the volume is equals to X squared times Z. And this is a fixed quantity here, so we can treat V as a constant throughout this problem. The total amount of materials is going to be the area of this, and this is going to be equal to X squared for the bottom, and 4 times XZ for the 3 sides. And this is what we wish to minimize. And if we can remove Z from the picture here, because what? Z is equal to V over X squared, and so that the area as a function of X is equal to X squared plus 4 XV over X squared, or 4V over X. Where does this make sense? Again here, X in the interval from 0 to infinity. But at 0, this is going to make the area very large as X is small, and when X is very large, this is going to make the area very large. So we can look for the minimum on some interval between 0 and infinity, and we can use the principles from before. Right? We want to find what the derivative is. It's going to be 2x plus 4v times minus 1 over x squared. And when is it equal to 0? When, what, 2x is equal to 4v over x squared, or when x cubed is 2v, or x is equal to the cube root of 2v. So x equal to cube root of 2v is the size that should make this. Right? And you make the resulting z so that the box multiplies to volume v. So it's the volume of the box. So that x squared times z is v. That's to say what? X squared z equals v, or z is equal to v over the cube root of 2v quantity squared. So here are the dimensions then of the box. Okay. Okay. I want to take a look now at an example that involves 2 variables, and sometimes it's possible to solve the Max-Min problems when you cannot reduce the situation to a function of 1 variable, but effectively you can. we're going to take a look at the situation with a box. The same problem as before, except now let's not assume that the bottom of the box is square. Box with an open top, and dimensions now x by y by z. And for simplicity, let's make the volume of this box 1. And the idea is to try and find the dimensions of the box where the surface area of the box is minimal. Okay, what do we have here then? We have x times y times z is equal to 1. And the area of the box is equal to x times y plus 2 times xz, one side here, times 2 plus 2 times yz. Okay, now, since you know x times y times z is 1, we can remove, let's say, z from the picture here, and we get that the area is equal to x times y plus 2xz is equal to 1 over xy, so that this is 2 over y. Plus, again, z is 1 over xy, so this is 2 over x. Now, you can't really hope to do any better than remove the z variable here, and you're still left with two quantities, x and y. And this is a situation here, I think, where you suspect that the best box really is the one with the square bottom. Okay, what's the story here, though? If we fix a particular value y, and consider this to be a y, then it is a function of x. And for this particular y, we could find the value where the surface area is minimal. We could find the value x where the surface area is minimal. Well, if we put that in here for y, then we would have only a function of one variable, and we could find where it takes on its minimum. So that's the game plan. So let's fix y, and then let's take the derivative of a sub y of x, treating y as if it were a constant, so that what? This is a constant times x in this case here, and the derivative is y, plus 2 over y. This is a constant if y is fixed, so the derivative of this is 0, plus 2, the derivative of what over x is minus what over x squared. All right, x to the minus 1, the derivative is minus x to the minus 2. So we want to know when this is equal to 0. All right, and it's going to be equal to 0 when y equals 2 over x squared. All right, and so this then tells us the value of y where this is minimal. So if we now put this back in here for y, we will then have one function, a of x. All right? And if we find out where it's minimal, that should tell us the dimension x that we should use for this box. So this is going to be equal to y is 2 over x squared, so x times y is 2 over x, plus 2 over 2 over x squared, plus 2 over x. Now we want to know when is this minimal? All right, well, this is what? 4 over x from these 2 over x's, and this is plus x squared. Okay, so we take the derivative of it, and this is 4 times minus 1 over x squared plus 2x. And so we want to know when this is equal to 0. And it's going to be equal to 0 when, what, 2 over x squared is equal to x. Or when 2 is equal to x cubed, or when x is equal to cube root of 2. So we've now found that x equal to the cube root of 2 makes this minimal. Now what should y be? Well, y is going to be 2 over x squared where this is minimal. And so y is equal to 2 over the cube root of 2, which is 2 to the 1 over 2 to the 2/3, which is 2 to the 1/3, which is also the cube root of 2. So y equals the cube root of 2 also, for this to be minimal. And now z, we can find out what z is supposed to be here because the volume of this box is supposed to be 1, so that x times y times z is supposed to be 1. Z has to be equal to 2 times the cube root of 2. Right. So this gives us the same solution we had before, but it also tells us that, all right, the best box here from the standpoint of minimal surface area occurs when the base is square. It was the best box with an open top. Huh? Okay. Okay, let's take a look at an easy example here then. Huh? Let's suppose that we want to take two numbers, x and y, greater than or equal to 0, and we want to find the minimum of x squared plus y squared when the two numbers add up to 10. So we want to find the minimum value of this. Okay, well, we have what? The sum, s, let's say, is equal to x squared plus y squared. We want it, this is a function of one variable, and so we've got x plus y equals 10, so y is 10 by this x, so that s is equal to x squared plus 10 by this x quantity squared. Now, what's the interval at which this problem makes sense? This problem here is defined so that x is supposed to be between 0 and 10. All right, then the derivative of s is 2x plus 2 times 10 minus x times minus 1. All right, and we want to know when is this equal to 0? Well, it's going to be equal to 0 when 2x is equal to 2 times 10 minus x. That's to say when x is 10 minus x, 10 is 2x, or x is 5. Now, when x is equal to 5, the value of y is equal to 5, and the value of x squared plus y squared is 50, 25 plus 25. Right? At the end points here, when x is equal to 0, or when x is equal to 10, x squared plus y squared is 100. So here's the minimum value here then. Namely, the minimum value occurs when x is half of 10, or 5. Let's take a look at another fairly simple example here. Let's suppose that we've got a triangle here. You can think of this as a triangular field if you want. And the idea is to put the largest possible rectangle in here, like so, or like so that the sides are parallel to these sides of the right triangle. Presumably a right triangle here, huh? And let's suppose that this side of the field is 50 and this is 100. Okay, well, let's put this in a coordinate setting here. Let's consider this to be x and y coordinates here and write the equation of this line. Well, what do we have here? Well, at this point, 50, 0 is on the line, and 0, 100 is on the line. And so consequently, this line should have a slope of minus 2. All right? And so we get, I'm using the slope y-intercept form here, I suppose. Y is equal to minus 2x plus 100. So that when x is 0, y is 100. Let's just check here. When y is 0, x is 50. Or when x is 50, y is 0. Okay, so this is the equation of the line. And now the point xy is going to be the corner of the rectangle, and so consequently the area of the rectangle is going to be x times y. Now we want this as a function of one variable, and so we can use this fact right here, that the area as a function of x is equal to x times minus 2x plus 100. Where does this make sense? X in the interval from 0 to 50. And it's clear that the endpoints are not where the maximum or minimum is going to occur. All right, well, actually, the endpoints are where the minimum is going to occur, because at 0, when x is 0, you end up with no rectangle to speak of. All right, and when x is 50, the same thing is true. So we want to find out where the derivative is 0. The derivative is the first times the derivative of the second minus 2 plus the second times the derivative of the first. Right? And when is this equal to 0? Well, when x minus 2x, or 2x, is equal to 100 minus 2x. Or when 4x is equal to 100. Or when x is 25. So that says that this should be, this side should be 25, and this should be 25. So that these two triangles here are going to be the same shape. X is 25, y is 50. That's where the maximum occurs. So let's take a look at one more geometrical type example, relatively simple one. Let's suppose that we've got a semicircle here. Let's say of radius 3, and we wish to put the largest rectangle in here, where the base of the rectangle is going to lie on the diameter of the semicircle, and it's going to fit inside of there. All right. Well, again here, it's frequently a good idea to set up some sort of a coordinate system. What have we got? The equation of the circle is x squared plus y squared is equal to 9. And so the semicircle is going to be equal to y. It's going to have for its equation y is equal to 9 minus x squared square root. Square root of that is going to be the positive square root. The negative square root would be the bottom part of the circle. Okay? And now a point xy gets to be on here if it's satisfied, gets to be a corner here if it satisfies this equation. And the area now, the area of the rectangle is given by 2x, times y. We want this as a function of one variable, and so we'll get that the area is equal to 2x square root 9 minus x squared. What's the interval on which this makes sense? Well, x could be as small as 0 or as large as 3. And it's clear that the maximum is not going to occur at either of these points here. Watch, when x is 0, this is 0. When x is 3, this is 0. So you get the minimum at those points. We want to take the derivative now. It's the first times the derivative of the second. 1/2 9 minus x squared to the minus 1/2 times minus 2x plus the second times the derivative of the first plus 9 minus x squared to the 1/2 times 2. All right, let's check this here. The first 2x times the derivative of the second, 1/2 9 minus x squared to the minus 1/2 times minus 2x plus the second times the derivative of the first. Okay. We want to know when is this equal to 0. Right. What's going to be equal to 0? I guess we can simplify this a little here. We get the 2 and the 2 here canceling. So we have minus 2x squared over the square root of 9 minus x squared. And now we've got 2 times the square root of 9 minus x squared. Let's put that over the common denominator, square root 9 minus x squared. So we're going to have 2 times 9 minus x squared over square root 9 minus x squared. Right, so this is going to be plus this. So this is going to be what? Minus 4x squared plus 18 over the square root of 9 minus x squared. We want to know when this is equal to 0, and it's going to be equal to 0 when the numerator is 0. That's to say when 4x squared equals 18, or when x squared is equal to 18 over 4 or 9 over 2. Or when x is equal to the square root of 9 over 2. All right, so the square root of 9 over 2 here. For x, what's y then? Well, it's 2xy is supposed to, let's see here. 2xy is the area. Y is the square root of 9 minus x squared. So that y then is equal to the square root of 9 minus square root 9/2 squared. So the square root of 9 minus 9/2, which is equal to the square root of 9/2. So y is the square root of 9/2. And that indicates that this rectangle is going to consist of 2 squares. These will actually be squares. The height y here is equal to the distance x there. So the maximum occurs when you place 2 squares in here.